Welcome to our third lesson as we review for our Calculus 1 course. This lesson is on function representations. The lesson will review the following concepts: the definition of a real valued function of a single real variable, independent and dependent variables, the domain and range of a function with some examples, graphical, numerical, and symbolic representations of functions, some graphing conventions, the vertical line test, and scatterplots of data and model fitting for data. The professor expects you to have some degree of proficiency in most of these concepts and techniques already. If you need more confidence in these concepts, talk to the professor. These essential ideas are presented at a collegiate level to reflect the precise and formal nature of mathematics to prepare you for this class and mathematics classes that follow. Calculus 1 is a study of real-valued functions of a single real variable. Generally, functions we study have the form y equals f of x. Here, f represents the function, and x represents the function's single real variable input. We call x the function's independent variable because we are free to vary it however we want. The y represents the output real variable of the function f. We call y the function's dependent variable because its value is fully determined by f and the value of x. A real valued function of a single real variable is a rule that assigns to each real number input exactly one real number output. In our course, inputs and outputs of a function will be real numbers, and the rule defining a function will be described by an algebraic functional expression of a single variable. This lesson will review common rules, e.g., families of functions, we will encounter in this course. Two special sets we associate to a function are its domain and range. The domain of a function f is the set of all possible inputs values of the function. The range of a function f is the set of all possible output values of f. On the next slide is a table with some important functions along with the domain and range for each. Note that R is the interval from minus infinity to infinity and means all reals. Take a moment to pause this video and review this table to assure yourself that you're familiar with most of the information. Recall the graph of a function f is the set of ordered pairs x, y such that y equals f of x and x is in the domain of f. Because the graph of a function could be infinite, for example, if its domain is unbounded, we aren't ever interested in looking at the whole graph of a function at one time. Instead, we focus on bits that interest us. Before we say more about graphs, it's good to recall Korbosinski's admonition that, quote, the map is not the territory, unquote. He was talking about maps of cities, subway systems, or freeway networks. He wanted people to recognize that an abstract representation of something shouldn't be confused with the thing itself. Pause the video and take a few minutes to think about this question. What are some ways that the graphs we draw differ from the function we are trying to represent? Miller likes to call graphs we draw in class cartoon representations of functions. Part of his reason for doing this is to keep things light, but another reason is to remind us that when we sketch the graph of a function, we're creating an approximate representation of a function that captures features that are important to us. In the next few slides are some conventions we use when graphing functions. When a function is missing a single number from its domain, its graph will have a hole that's only as wide as a single number, or it'll have a vertical asymptote. Here's how we draw them. On the left is the case where a graph is missing a single number, and an open circle represents that hole. On the right, the graph is missing a single number, but at that number is a vertical asymptote. The open and closed dot convention is also used when a function's graph has jumps or breaks. On the left is an example of a jump discontinuity, something we'll study more in this course. Note that the function can only have one value at the input x equals 1, so at most one endpoint of the jump can be a closed circle. The graph on the right has a point discontinuity. Another symbolic representation we'll see when we use the cosine function to represent dense oscillations near an input value. On the left is the graph of the cosine function, y equals cosine of x. On the right is the graph of the function y equals cosine 1 over x. What's happening on the right is that the infinity of oscillations in the cosine function from x equals 1 to infinity are put into the interval from 0 to 1. So in the picture on the right is an infinite number of oscillations near the y-axis. No computer could perfectly render a dense oscillation like cosine 1 over x near x equals 0, nor could any human eyes discern it if a computer could draw it. So we're comfortable with the cartoon rendering of this behavior pictured here. And you just need to recognize when this is happening. A final note on graphical representations of functions. Not all curves in the Cartesian plane represent the graph of a function of the form y equals f of x. Because a function assigns to each input x exactly one output y, we can test a curve to determine if it is the graph of a function using vertical lines. And here's the vertical line test. If every vertical line intersects the curve in at most one point, then the curve is the graph of a function of the form y equals f of x. The set of points satisfying x squared plus y squared equals 1 does not pass the vertical line test, for example. Numerical representation of functions. If your major is among the empirical disciplines, like chemistry, biology, political science, you are more likely to encounter functions in a numerical form. Numerical representations of functions are often presented in a table, for example, a spreadsheet, or in a table of ordered pairs. Here are two examples of how data might be presented and how we can interpret data. The first example shows a scatter plot of numerical data in the table below, and it shows that y is a linear function of x. Specifically, this data shows that all the ordered pairs fall exactly on a line of the form y equals mx plus b, and the slope and intercept of the line can be calculated directly from the data in the table. Pause the video and convince yourself of this. A scatter plot of the numerical data in this example shows that y is approximately a linear function of x. This means that the points fall near the graph of some y equals mx plus b. The m and b can be calculated from the entire dataset using a process called linear regression. Pause the video and convince yourself that the data is not exactly a line. When we get data from measurements of real-world phenomena, we need to go through a process of model fitting. This is the process that identifies a function that describes one variable's values in terms of the other. Linear regression is one example of model fitting. Models give us a way to interpolate data, finding input values for input values between those in the dataset, and to extrapolate data, finding output values for input values outside the range of given inputs. Models are powerful and important, but just like they say that the map is not the territory, they also say, quote, the model is always wrong, but often useful. Symbolic representations. This course will focus on using calculus to study symbolic representations of functions. From prior coursework in mathematics, you should be familiar with the following types of or families of functions: polynomial functions, rational functions, algebraic functions, i.e. polynomials with rational exponents, exponential functions, logarithmic functions, and trigonometric functions and their inverses, along with algebraic and functional combinations of these. We will review each of these families in the next 2 lessons. This lesson has reviewed the following concepts: the definition of a real-valued function of a single variable, independent and dependent variables, the domain and range of a function with some examples, graphical, numerical, and symbolic representations of functions, some graphing conventions, the vertical line test, and scatter plots of data and model fitting for data. These essential ideas are presented at a collegiate level to reflect the precise and formal nature of mathematics to prepare you for this course and for other mathematic courses you will take afterward. All right, see you at the next review.